Wanted to work through the worksheet involving a diffraction grating and looking at white light in a diffraction grating and looking at how the diffraction grating spreads the white light out into the rainbow of colors from red to violet that make up the white light. Now, I don't actually have the diffraction grating with me, so I'm not going to look through the diffraction grating and sketch the diffraction grating pattern. I'm going to calculate the diffraction grating pattern that you have sketched in the worksheet. A diffraction grating comprises many thin slits that each act as a source of light. When you shine light on the front of the thin slits, the light emerging from the back of the diffraction grating is diffracted, and those diffracted light rays from each of the slits interfere with one another. When you get constructive interference of all the light coming from each of the slits, you get a bright line in the diffraction grating at a certain angle, a bright spot from the diffraction grating at a certain angle. There's an equation that describes the location of the bright lines or the bright fringes or the bright spots. It's an equation that relates the angle at which they occur at to the wavelength of the light and also to the separation between adjacent slits. It's d sine theta equals m lambda. So in that equation, theta is that angle at which you get the bright line or the bright spot. Lambda is the wavelength in, say, meters. And d is the separation between adjacent slits. That's also in meters. And then m in that equation is an integer. If m is 0, that's just a bright spot in the center of the screen or a bright spot at 0 degrees. M equals plus or minus 1 are the first diffraction maxima away from the central spot. And so we'll see a rainbow of colors associated with m equals plus or minus 1. M equals 2, that's the next diffraction minimum away from the bright spot and away from the first diffraction minimum. Again, you'll see a rainbow of colors at that angle corresponding to the different wavelengths. And that's basically how the equation d sine theta equals m lambda describes the spectrum, the light that's produced by the diffraction grating. Now, the first diffraction grating you use in the worksheet is a diffraction grating that has 300 lines per millimeter. And we're going to calculate, or I'm going to calculate, the m equals 1 constructive interference, the angle of the m equals 1 constructive interference for the white light, which is composed of wavelengths from red light to blue light from 400 to 700 nanometers. And then I'm also going to calculate the kind of second rainbow. That's the m equals 2 constructive interference of the white light comprising the wavelengths from red light to blue light from 400 to 700 nanometers. So I'm going to do those two calculations. You have 300 lines per millimeter, which is a separation between individual lines. If I divide the number per millimeter by, if I divide 1 by that number per millimeter, I get the separation between individual lines. And that comes out to be 3.3 times 10 to the minus 3 millimeters, or 3.6 times 10 to the minus 6 meters. That's actually 3.3 microns. So there's a very narrow separation between adjacent slits. I'm going to start with the red light, and I'm going to start with the m equals 1 constructive interference, the m equals 1 bright lines, and we'll calculate the angle that occurs at. And then we'll move on to the m equals 2 red light bright line. And there was what changed to the blue light, the wavelength of the blue light, and the m equals 1, m equals 2 locations for the blue light. So here's lambda subscript r. The red wavelength is 700 nanometers. That's 7 times 10 to the minus 7 meters. And here's the index, m equals 1, plus or minus 1. Then we're going to calculate the angle for this particular constructive interference. The equation I'm going to use, d sine theta, we want theta, equals m lambda. And we know d, we know lambda, and we know m. So I've just got to rearrange this. Theta equals the inverse sine of the ratio of lambda to d. And I've plugged in the fact that in this case, my m is 1. And if I fill in lambda, that's 700 nanometers. Well, that's 7 times 10 to the minus 7 meters. I fill in d. That's 3.3 times 10 to the minus 6 meters, 3.3 microns. And if I take the inverse sine of that, I got a angle, which is 12.2 degrees. So that's the angle for the red light, where we see the first bright red light line away from the central maximum. For m equals 2, let's do the same calculation for m equals 2. So I mean, here, m equals plus or minus 2. We're going to do the same computation. We're going to use this same formula, and d sine theta equals m lambda. We're going to rearrange it again. We want theta. Theta will be given by the inverse sine, arc sine, of the ratio of m lambda, which is 2 lambda this time, because m is 2, to d, the slit separations. And so I've just got to plug in 2 times 700 nanometers, or 7 times 10 to the minus 7 meters, divided by 3.3 times 10 to the minus 6 meters, the slit separation, that's 3.3 microns. And that number came out to be 25.1 degrees. So this is the red light, the location of the bright red bands for the red light. They're on either side of the central maximum. To the left and to the right, there's a bright red band at 12.2 degrees. And beyond that, to the left and the right, there's a bright red band at 25.1 degrees. They correspond to m plus or minus 1, m equals plus or minus 2. Now let's do the same calculation for the blue light. The blue light has a wavelength that's 400 nanometers, or at least we're going to call that blue light. And we want to do the same calculation for m equals plus or minus 1 and m equals plus or minus 2. So, same idea. We're going to use this master equation that d sine theta equals m lambda, but we'll be applying it for the blue light. And if I rearrange it again, the angle theta is going to be the inverse sine of lambda. Now it's the blue light lambda divided by the slit separation. The lambda is now smaller for the blue light. It's 400 nanometers rather than 700 nanometers. So the angle is going to be smaller, and the angle I got was 7.0 degrees. So that's the location of the m equals 1 blue light. It's inside the red light. So if you walk away from the central maximum, you're going to first find the blue light of the rainbow, and then you'll walk your way through green and yellow and orange, and you'll find the red light. I've got to do the same calculation for m equals 2 plus or minus 2. Again, it's all down to this master formula related the angle to the wavelength and the slit separation. D sine theta equals m lambda. We rearrange for theta. So theta is going to be the inverse sine, this time of 2 lambda, where lambda is the blue light. 2 is because we're thinking about the m equals 2 maximum divided by d. And I've already calculated this. This came out to be 14 degrees. Okay, I'm going to make a sketch down here of this rainbow of colors that we see in our diffraction grating. The horizontal axis here is the angle. 0 degrees is in the center. This is, say, the center of the screen, or undeflected light. This is where the m equals 0 light will form a constructive maximum. I'm going to first start by sketching the locations of the red maxima, the red lines, and then we'll add to it the locations of the blue line. So the red line will form a maximum at 0 degrees. That's m equals 0. But then it will also form maxima at the angles that we calculated for m equals 1 at 12.2 degrees, and for m equals 2 at 25.1 degrees. So we've got to add those maxima. Here's the m equals plus 1 at 12 degrees. Here's the m equals minus 1, let's say minus 12 degrees. Here's the m equals plus 2 at about 25 degrees. Here's the m equals minus 2 at about 25 degrees, minus 25 degrees. So these are the locations where we'll see bright red light. Now for the blue light was 400 nanometers, if you remember. Because of the shorter wavelength, the angles of the bright lines are smaller angles than the red light. There's going to be a bright line at 0 degrees. That's also m equals 0. And there's going to be then m equals plus or minus 1 blue lines at 7 degrees. So that's somewhere in here and somewhere about here. This is 7 degrees and minus 7 degrees. And then also at 14 degrees. So 14 degrees is going to be somewhere over here on the right and somewhere over here on the left. And so these are the m equals plus and minus 2 blue lines. The rainbows themselves fill in the regions from, remember the blue has the smallest angle for a particular maximum, and the red has the largest angle. So the m equals 1 band or rainbow is this region here on the right-hand side, and also this region here. This is the m equals minus 1 band on the left-hand side. So let me mark that. M equals 1, m equals minus 1. And then the m equals 2 band, that's again, remember blue, smallest scattering, or smallest angle for the constructive interference, and red, largest angle for the constructive interference. So m equals 2 rainbow is over here in this region. This is m equals 2 plus 2 on the right-hand side. And this will be m equals plus 2 minus 2 on the left-hand side. So this is the spectrum of light that you'll see in the diffraction grating with 300 lines per nanometer. We also, in the worksheet, are asked to work out the pattern that you see with a diffraction grating that has 100 lines per millimeter. So this one has a smaller spacing between the lines. The 100 lines per millimeter has a larger spacing between the lines. So this one has a smaller value for D. The 100 lines per millimeter has a larger value for D. What will that do to the angles? Well, in each case, if you look just down here in our calculations, we're always dividing by D. So D was 3.3 times 10 to the minus 6 meters for the 300 lines per millimeter. So D was always that value, or 3.3 microns. When we have 100 lines per millimeter, D will be 10 times 10 to the minus 6 meters, or 10 microns. So it'll be about 3 times bigger that we're dividing by. And that means if we're dividing by a number that's 3 times bigger, the argument of the sine function is going to be 3 times smaller. It means these angles will be smaller too. So for the 100 lines per millimeter, I won't redraw it. This whole pattern, the pattern will stay the same pattern, but it's going to be compressed from this range that goes out to about 25 degrees to a smaller range corresponding to the greater distance between adjacent diffraction gratings, adjacent slits in the diffraction grating.